Yeah, hello and welcome to our third part of this online training. My name is Daniel and I am happy to present you as an organizer this training. I'm responsible for the human resources here in Germany, for German employers, and also for the marketing and a little bit for the customer support. With me in this online training is Ayla. Ayla, if you want to introduce yourself.
Yeah, of course, Daniel. So hi everyone, good morning. I want to welcome you as well for today's online training. And my name is Ayla. I'm joining this training today as a co-organizer, assisting Daniel and answering any questions you may have in the chat. And I will also try, like, if some questions are asked several times, and if we have time enough, I will interrupt Daniel to show you that a second time. If not, I think we are recording this training, so you will be able to watch it once again. And I'm sure that you will learn a lot of interesting as well as new things today during this online training. So have fun. And with that said, Daniel, back to you. So I guess we can move on, right?
Yes, thank you, Ayla, for that short introduction. So let's skip to the next slide. For those who are visiting the training or this webinar for the first time, short information about GoToWebinar. We use this tool for our presentation of these trainings. First of all, here you can see you can show or hide your control panel. If you can't listen us, please adjust your audio settings maybe, adjust your speakers. And if you have any questions, you can ask this here in this text box. And yeah, let's jump to this webinar's content, to this online training content. First of all, we model and design today a timber truss girder. The next part will be the modeling and design of a steel hull with concrete columns. And the last part of this training will be the design of a concrete building, which you see here on the right side. Yeah, and these three projects we will do together. So I close my webcam. I jump to RFEM. So now it would be interesting for me who is modeling also with me. So please put your hands up in this GoToWebinar tool. I think that should be possible, that I can see that someone is doing this. You can raise up your hands here in this GoToWebinar tool. Yeah. Some people are modeling with me, so I adapt my pace. Okay, good. Let's start with that. So first of all, this timber truss girder. I want to model this timber truss girder in 2D XZ, so it should be an in-plane girder. So first of all, the model name is timber truss girder. I choose the right project name for that. I choose generally my download folder, and important 2D. And I want to create my combinations automatically, but not the German national annex, just the normal Eurocode. My positive orientation of my global z-axis is downwards. So after that, I click on OK. And you will see here our work plan. Additional hint on that place is that you will get the recording of this training. You will get also a certificate and also the training materials after this training per email. So at first we want to create this girder, this truss structure. So for that we go here to the menu bar and click on Tools, and then we can generate models by members, and here we can choose 2D truss. So I decide for that type of diagonals because I want to transfer here tension loads or tension forces in that diagonals. So I choose this type of 2D truss. My number of bays is 10, and the total length of this girder is 60 meters. And the total height at that point here in the middle is 5.753 meters. And the side height, so on the left or on the right side, is 2.6 meters. Good. Now I have to create new cross sections with the right material. So for the upper chord, for the lower chord, diagonals and verticals. So for that, for the upper chord, I don't know the right pronunciation, sorry for that. I choose a new cross section. I think the right word is chord. So
yeah, I guess so. It's chord.
Okay, thank you. Thank you, Ayla. So I create a new chord and I choose here a rectangular chord because we want to create a timber chord. So I click here on that icon, and my parameters for the width and for the height is here 220 millimeters, and for the height it's 520 millimeters, so 52 centimeter and 22 centimeter. Now important is that we choose here the right material, and here you see I just have the concrete and the steel, but we want to have here also a glue-lame timber. So we have to create a new material, and here we create this new material when we click on this material library. So I choose here timber, and this mask jumps to the normal timber materials. And now I choose here glue-lame timber because we want to have more characteristic strength and also the right standard, in this case the Eurocode, and I choose here the GL28H. Yeah, so you will see here characteristic strength for bending. I think that's pretty clear when you visited the lecture of timber structures in your study. 2.8 kilonewton per square centimeter. Click on OK, then again on OK. Yes. And you see here the upper chord has changed to this cross section. So, and let's do the same thing for the lower chord, for the diagonals and verticals. For the lower chord, I choose also a cross section, but in this case 220 and 560. And material is the same. Now I can copy here this cross-section description with Control key and pressed C key. Click on OK. and I create a new cross section for the diagonals. And now I copy here this thing and choose here the right material and change here the cross section to 200 and 200. So we have a quadratical cross section here. Click on OK. And now the same thing for the verticals. And here we have a cross section of 200 and 180. Also material glue lane timber. So now on the right side, you see the different member types, beam and truss. Where is the difference? Beam can transfer all typical internal forces like bending moment, normal and shear forces, and truss is a member type that has on the end of a member hinges, yeah, and therefore you can transfer only normal and shear forces, no bending moments. So keep that in mind. I click on OK, and you will see here this truss girder. Yeah, so the next step is that I want to adapt my grid to the size of our model. Yeah, for that I click with the right mouse click, and I can choose here on work plane grid snap. And here I have the possibility to adapt my grid according to size of model. Yeah, when I click on that, you will see that the whole grid system adapt to the whole size of my model. And this makes, in my opinion, the overview of the whole model and project a lot of easier. So the next step is that we delete here the left members and the right members, because I want to create here a support, single support. So I draw a selection window from the right to the left side, and the same thing on the right side. And then I can click here, right click, and say delete. Now these 2 or 4 members were deleted. And now a very important point, because I want to transfer here also some forces, that we change here these diagonals to the member type beam. So I select this diagonal, press the Control key in order to add something additional to the selection, press this diagonal, then double click with the left mouse click. And now I change the member type to beam. Good. I click on OK. And when I change here on the menu symbol bar the display model to a wireframe display model, you see here this set of members. Yeah, set of members. It's when you want to summarize some members, you can use the function set of members. Yeah. And I want to add these members to that set of members. Therefore, I double click on this set of member, and I add here this additional diagonals to that set of member. For that, I click here on this icon, select members, click on that diagonals or on that members, click on OK. And you will see here this set of member. Yeah, so you see this program created automatically this set of members by generating this 2D structure. And this will help us later when we want to add some loads. Good. Yeah, the next point is that we add here some single supports. Yeah, so we select here through this selection window this node, and after that we click here on the symbol bar, new nodal support, and this support should have this type hinged, and on the right side we have another support, and this should be a support which carries only vertical forces. So I move this with this selection here on UX away, so that we just activate here the vertical forces, similar to this sliding in X direction. Good. So I changed the display model, and now we see here this truss structure. So very interesting. Here, these diagonals can be a little bit too thin, yeah, but I want to modify them after the design or after I see the internal forces, because when I get here vertical forces on that upper chord, I'm pretty sure that this lower chord will get a lot of tension forces, because these truss structures transfer mostly these compression and tension forces. But we will see this after the calculation. Good. Yeah, the next point is adding some load cases and loads on that structure. So for that, I click here on new load case here in the symbol bar. And the first load case description is here, self-weight plus roof load. Yeah. Then I click here on create new load case. And the next load case is snow. And I want to consider the snow loads once on the left side and once on the right side. So for that, I click here, I enter here left. Then I can easily copy this load case by clicking copy selected load case and create new. And here I change the name from left to right. And the last load case is wind. And suction, because we want to consider also a suction wind load case here on this upper chord. Okay. Important thing is here, because we activated here on this basic data at first, that we want to create this load combinations automatically. So several register open here, and we have additional options to do something. Like here for the snow, for me it's important that the acting of the snow action is simultaneously. That means that both load cases can combine to each other. Yeah. So no one exclude each other. We will see that later on that load combination. I click on OK. And now I can create here the load cases or the loads. So for that, I can click here on New Member Load. And now, because we have this set of members, we can refer to them. Just click here on Sets of Members, and then the load parameter is 2.5 kilonewton per meter, and I relate to the true member length, because we have here an inclined member. So for self-weight, it's important to select here this option, global related to true member length. I click on OK. And now see and watch, I can just easily click here on this set of member, and the whole load will be created on that upper chord. It's a really big advantage of this set of members when you do that. So the next point is the snow load case. And as I said before, we want to create here this one on the left side and after that on the right side. Now we can't use this set of members, but we can easily select these left members by drawing this selection window. So just do this selection window and you will see, okay, these members are selected. Then click here on New Member Load. And you will see here that this load refers to the members from 1 to 5 because we selected them before. Load parameters 3.75. And also here, in this case, relate to the projected member length because this is the normal snow load here. Yeah, important to know that. And we do the same thing on the right side. So also here, new member load, same load parameter, same options, click on OK, and we've done it. Good. Next load case, wind suction. So I want to create here wind loads. For that, clicking here again on member load. Again here, I refer to sets of members. And now important point, I want to refer to the local related of the member length. Yeah, so to the local axis of my members. And because we have suction forces, so suction loads, I have to enter here negative load parameter. And the load parameter is here minus 2.4 kilonewton per meter. I click here on that upper chord and this creation of our loads is done. Yeah. When you want to know the local axis of one of this member, no problem. Click with the right click of one of the member, say local axis system of members on, and you will see here the local axis coordinate system of the members. Good. I deactivate this again because I know my system. And now we can calculate this. And now go to the load cases and combinations again. Click here on load cases and combinations. And look for the combination expressions. Here you see the ultimate limit state and also the serviceability state. Yeah. For that easy and simple design of this truss structure, I don't need this serviceability expressions combinations. So I select them all by holding the Shift key and delete them. I have just interest in this ultimate limit state because in this case it's more important. I jump to the next register, action combinations, and here you can see the different action combinations with the leading load case, yeah, by this by this combination value 1.5, and here also the other leading load case. In this case, here we have the wind load case as the leading load case. The load combinations we can see here. I think this is pretty clear. And as I said before, we have activated in the register actions both load cases of wind, yeah, and this means that they can act together. And this is important to know, because when we activate here at the snow action alternatively, this would mean that both snow load cases would exclude each other. Yeah. Good. I click on OK. And now I can say, okay, calculate all, please. And after that, let's watch the results of this girder, of this truss girder. Yeah, the calculation will take some time. I think that's pretty clear. And yeah, here we can see the deformation. We can display the deformation a little bit nicer. Just click here on the display navigation bar, go to results, and click here on the area deformation, members, and cross-section colored. Good. But I have more interest in the internal forces. And for me, very important, and now you can see it, the bending moments aren't so important at that truss structure. Yeah, you see it here. Yeah, there are some bending moments, but they are not very high. But when we look to the normal forces, they are very high. Look at that here, 900 kilonewton. Really, this is really much. And here again, compression forces in this upper chord, yeah, 900 kilonewton. Yeah, this is really much. And I think there will be a little problem of that small member diagonal, 600 kilonewton as tension force. I think there we will have some problems, but we will see it after the design of that members in the timber design. Good. So now let's come to the design of this timber structure. For that, I jump to the data navigator, and when you scroll down, you will see here our add-on modules. Yeah, these add-on modules enables you to design almost everything according to some standards. So with the normal RFEM, you can calculate all structures, but if you want to design something, you have to use our add-on modules. And because we have here a timber structure, I have to use RF Timber Pro. you will find it here, somewhere there. I can add some add-on modules as a favorite one, and they will be here. And now I click here on RF Timber Pro. So this enables the design of timber structures or of timber constructions. And now I have the possibility to choose my members or my sets of members which I want to design. So at first I want to design here my upper chord and my lower chord. So how can I do that? At first, I don't want to design members. I want to design, as I said before, my set of members. So just select the upper and the lower chord, click on OK, and choose the right standard. Yeah. In this case, we refer to our Eurocode standard and no German national annex, just the European, so the normal Eurocode standard. If you want to see more details concerning some values here, you can see it here by clicking on that icon, and here you have some additional informations of how they calculating some limits and some designs. Yeah, good. Now important, I have to select the right combinations or result combinations for my design. I decide here to design my load combinations. I choose here every load combinations and transfer it to the right side. Select it for design. I just design here for the ultimate limit state. We don't need any serviceability limit state. Good. Now jump to the next to the next window, and here we see the material timber for the design. Here we can see some material properties, characteristic strength for bending, for example, or for tension, compression, and so on. Let's jump to the cross sections. Here we can see some cross sections which will be used for the design. And here, additional note of 7, no member with this cross section is selected for design, because we just design here the upper and the lower chord, and the verticals aren't selected for that design, because we can create here after that several cases for our design, but we do that later. Now, important point, load duration and service class, especially for the timber design. And here we can see it. Self-weight and roof load is permanent, and our snow load cases are short-term, so the load duration class, important for the timber design. And here we have also this service class. I decide here for the service class the second, and so we have here some additional information for the service class 2. And now I go to the next window, effective lengths. This is very important when I want to do some stability design. And now I assume, or I assume that my upper chord is fixed enough due to additional due to additional members out of the plane. So I assume that this is fixed enough. So I say that no buckling is possible for the upper chord. And for the lower chord, you see we have just tension forces, so no stability sign will be necessary because we have to consider stability only if we have compression forces. And the only compression forces you will see here in this upper chord. And so for tension forces, we don't need to consider any buckling or torsional buckling. So I don't select here anything. I can do the same thing when I click here on details. And when I jump to the stability register, I can say, okay, please don't consider any stability because I know, okay, my upper and my lower chord are fixed enough, or the stability wouldn't be important here. Same solution. Parameters, I can here add additional additional parameters, but in this case, this isn't so important. So how I can calculate this? And now you can see here two different windows. First of all, here at the results, these results are listed in different categories. Here, design by load case, cross-section, set of members, and so on. I choose here by cross-section, and almost everything is fine, except here this rectangle 200 by 200. And I'm pretty sure that this is this diagonal here on the left or right side. So I can filter them a little bit better. I click here on this rectangle and I can see here, okay, this this member, this diagonal is not good because our cross-section resistance, our design is over 1. And when I click here on this rectangle, I can see here the design ratio, and that this design ratio is more than 1. Here I can see the whole way of the calculation of this design. And what can I do? I'm pretty sure that we have to increase here this this cross section. How we can do that? Just go here to cross section and activate here optimize and click here on yes. And now you can say what you want to optimize. I want to optimize the height of this cross section. So I click here on height. The width should be the same, just the height. And I know the height, they can start at the minimum of 200 and the maximum of this height should be 440, and the increment of these steps should be 20 millimeters. I click on OK. Then I click again on the calculation, and now you see the designs are good enough. At that moment, the design ratio of the new cross section, and here we can see, is 220/20. Good. Now it's important that you transfer also this new cross section to export this cross section to RFEM. Export cross section to RFEM. Click yes, because now it's important to calculate the whole structure in RFEM again, because we have new stiffness here in that case. So calculate everything again. Okay, now let's go to the results of our add-on module, RF Timber Pro. And here we can see the max design ratio is 0.99. This is very good. Good. Now I want to design the verticals, and after that the diagonals. So I click here on new case, and the description of the new case is the verticals, because now I want to design the verticals. Click on OK. I select the members for the design, and now I can click here every vertical manually, or I use a more smoother way of selection. Here in the symbol bar, I have the option to select special objects here in RFEM. I click on that. And now I choose here, I activate here this member. Scroll down and say, okay, parallel to member. Now I choose this one member. Click OK, and you will see all members are selected parallel to that first member. I click OK, and these selected members were transferred here to that part. So again, I choose here my load cases for the design. I go to materials. I think this is now pretty clear. Cross sections and so on. Effective lengths. Oh, sorry, here I have to select the service class to 2. And now important here we can get some pressure forces. Yeah, when you watch here we have a vertical of some compression forces. Yeah, and here I want to consider the stability design. And because I have here the normal buckling, once in out of plane and once in plane. So the normal Euler case 2, I say, okay, my length, my buckling length should be the same as the member length. Yeah, also for the lateral torsional buckling. So the inputs of this length are enough, and I can say, okay, calculate. And again, I see, okay, all designs are are fulfilled. Good. Now the last case is the design of the diagonals. So new case, diagonals. Click on OK. And again, I choose here the right members for the design, and I want to design here this member, the diagonals. Now it's, as you can see, a little bit hard to select them because clicking the same time is a little bit hard. So I use here my view navigator, and I want to display them by different cross-section types. So members by cross-section. And now I decide here for the T rectangle, 200 by 220. and I choose here this these members. Click on OK. The members on the left and on the right side I don't want to consider because I have already considered them in the design of the lower and upper chord. So in the first case of this design, click on OK. Choose here the right load cases for the design. Jump to the next window, materials. I think here is pretty everything clear. Cross section, also here is everything correct. Load duration class, yeah, the same things here again. Maybe the service class, change here to 2. Effective lengths. Again, I suppose here the member length as the buckling length, because I say, okay, out of plane and in plane should be the same as the member length, because I suppose here this Euler case 2, and I say calculation, and all proofs are fulfilled, are correct under the design ratio of 1. And yeah, this was the very easily design of this timber truss structure. We can also watch the different design ratios graphically. So I click here to RF timber, and here we can see the different design ratios. And yeah, as we supposed correctly, this diagonal here on the left and here on the right side has a very high design ratio in comparison to this normal lower chord. But I think that's pretty clear because here we have a smaller cross section, like here on this upper chord. Jump to the next design case. So the verticals, and here the diagonals. Yeah, this was the design of this timber truss structure. Good. Ayla, any questions or anything to show? What would be good?
No, I think everything is fine and nothing special.
So to the attendees, you can ask us almost everything. We try to answer them. Don't be shy to ask something. We are here to help you. We are here to show you the solutions. Yeah.
Okay, we have one question. How to achieve optimum design?
Yeah, that's a good question. As a practical or for every structural engineer, the optimum design depends on several points. For one structural engineer, the optimum design can be the lowest cost of material or the lowest weight of materials, the best structure. It is hard to say what should be the optimum design of this truss structure here. But from the practical, someone could say, okay, the optimum design can be that everything here on this truss structure is nearly at the near of the design ratio of 1. So when I jump back to this design ratio, we can say, okay, maybe we can design here this lower chord nearer to the design ratio of 1. Yeah, it's not so easy to say, but again, you can optimize here the cross sections. So when I jump to the first case, you can say, okay, maybe I can optimize here this upper chord. So I can say yes. I just want to optimize the height. The width should be the same. I start with the height of 220 and the maximum should be 500 and the increment 20 millimeters. And the same thing I can do for the lower chord. Here also just the optimization of the height. Increment 20 millimeters, important for the production of this cross sections in the factory. I say, okay, calculation. Okay, now you see here the design ratio 0.99. And when I jump to the cross sections, I can see, okay, here cross sections by the design of timber structures 220 and 300. Okay, but consider when you calculate this again, you will get more deformation, and we didn't make any proof of the deformation. Yeah, just the ultimate limit state. Yeah, this is something you have to consider when you do this design, because when I say here, okay, export all cross sections to RFEM, and I say yes, you will get higher deformations because now our structure is thinner, I would say. Yeah, you have smaller cross sections, so it's not so stiff as before, and you will get pretty sure higher deformation. Yeah, let's look to the deformation, maybe on that load case. What's that? Maybe this would be more interesting when you have just vertical loads. And I remember that we have a deformation of 180 millimeters. And now we will get deformations of 260 millimeters. So 8 centimeter more. I don't know. This is also something you have to consider in your design. Good. Anything else, Ayla?
Not yet, no. Okay, we have one new question. Is it possible to have multiple sections for each member?
Yeah, that's possible. Yeah, but you have to create for different members more cross sections and put them to the design. Yeah, that's possible. Yeah. So I can, but we almost did here the same thing. So we designed here for that upper chord a different cross section, for the lower chord a different cross sections, for the verticals. Maybe you can optimize your construction for the verticals and the diagonals, because here you will get more tension forces. So you can say, okay, the first 2 rows of this diagonal can be a different cross section and put them then to the design. But consider also the production in the factories of this structure. Yeah, when you say please do every cross section different, the factory of this structure will say you wouldn't be it more economically when we have similar cross sections. Yeah, this is possible. Yeah, but also consider the production and manufacturing of this truss structure. Okay, then I would say let's make a break, coffee break of 5 minutes, and we will see us at 10 o'clock or in 5 minutes. Okay, so see you soon. Okay, so let's continue. Ayla, are you here?
Yes, I'm here.
Okay, very good. So let's start with another example. For that, I create a new model. And here I want to model and design a hole or a steel hole. I choose here type of model 3D, and I do the classification of load cases and combinations to the normal Eurocode. And my positive orientation of the global z-axis is downwards. So I click on OK. So again here, we have here the model type 3D. So we have here in that symbol bar, you can see it here, 3 different work planes. Now I click here on the work plane XZ because first of all, I want to create a 2D truss structure. Again, as before, click here on the menu bar, tools, and go to generate models, members, and click here on 2D truss. So again, I want to transfer my normal forces here with that diagonals in that directions. So my truss structure will get here tension forces. My number of bays are 6. The total length of my truss girder is 18.75 meters. Total height 3.25 meters, and the side height is 20.75. Yeah, now we have to create new cross sections, but I think that's at the moment known how this works. So I create new cross sections. The upper chord has a cross section of HEA 300. So here, click here, import rolled cross sections, HEA 300. And you see here the cross section description. The same thing with the lower chord. I can enter here also the name. This will be much faster. Here we have an HEA 280. I have to choose the right material. Diagonals, IPE 160. Again, I choose here the correct material. And the verticals are HEA 160. Good. I click on OK. And the next part is that I change here this outer diagonals because I'm pretty sure that they will get more internal forces, so especially normal forces. Therefore, I change here the cross section. I select them, double click on one of them, and I change here the cross section. And here I change the cross section to HEA 140. I choose here the right material. and click on OK. Good. So now we have different types of cross sections. We can display them a little bit nicer. I can show you how it works. When you go to the display navigator and you scroll down, now you have here the possibility that you can color the graphics according to the cross section. And here we can see the different cross sections by different colors. And if you want to change maybe one color, no problem. Click here on the right side on this panel. By double click one of these cross sections, you can easily change the color of one of them. So if you don't like this blue color, you like, for example, this violet, just here this one, you can change it. Yeah, good. Or blue, I think that's more blue than violet. Good. So next step is moving this truss 8 meters along the z-axis upwards. So select everything, right click, click here, move or copy. I just want to move it 8 meters high, so I don't have to enter here the number of copies. Displacement vector, remember our global z-axis is downwards, so I have to enter here when I want to move it upwards, minus, so negative value, -8. So, and the next part is that I delete here this outer verticals because I want to connect here a concrete column. So I delete here this outer member. Now I create a new column. For that, I click here on the symbol bar, new single member. I create a new cross section, rectangle and quadratical cross section, concrete C3037 according to the Eurocode. I click on OK. Again on OK. And I start from the button to this corner node of this truss structure. Now you can see I can't snap here these grid points because I didn't activate this here. Here on this status bar, you can activate here snap to grid. Now it's activated and I can snap here these grid points. Good. Now I copy it easily by drag and drop by pressing the Control key on my keyboard. And because they have here, in this case, the same colors, I change here the color of my concrete structure to pink. So, nice. Good. The next part is that I adjust here some hinges. Yeah, and we offer two ways of insert of hinges. The first thing is, maybe this is also not so known, that we can add hinges graphically. Therefore, go to the menu bar, insert, model data, and then go to member hinge, and then assign to members graphically. As you can see here, I want to connect this upper chord by a moment hinge here on that concrete column. Therefore, I create a new hinge type and I activate here the moment hinges. I can also do it here by clicking on one of these icons, set rotational release MY and MZ. Yeah. It's the same solution. I click on OK, and now you will see here blue nodes or circles. When I click in the middle of one of this member, the hinge will be created on both ends. And when I just click here of one of this member end, it will create this member hinge just at the end of this member. Yeah, I do it here on the left side and once on the right side. Click on OK. I change here the display model to the wireframe model, and you will see the hinges a little bit better. And the same thing we do for the upper chord. The other way of this member hinges is just click here by double click of one of the member and adjust here the member hinge. And here in this case, I want to create a member hinge which has moment hinges, but also a shear and normal hinge, because I want to transfer all these forces via this diagonal. So I create a new hinge. And because I don't want to transfer here at these ends some vertical forces and normal forces and also bending moments, I have to activate here the movements UZ and UX. Click on OK. And after the calculation, we can see that the tension forces in that upper chord are transferred to that diagonal into that column. Because when we have here tension forces, this tension force will go along this diagonal and will transfer this tension force as a compression force to this concrete column. I think that's pretty clear. Then the right member. And here the same hinge, but at the end. Good. Yeah. The next part is that we check the self-weight of the structure and watch the internal forces if this frame is is modeled correctly. So for that, I choose here also the lower nodes because we want to create now some supports. We have a rigid support here. So this enables me the activation of all moments and vertical and horizontal forces, reaction forces. Now I create here a new load case. Self-weight, and just I activate here the self-weight, click on OK. And now I want to see the results. So, okay, I think the deformation, here we see at first the deformation, but for me more important, the internal forces. If we modeled and entered here the hinges correctly. So for that, I activate here the internal forces. And yeah, here we can see it. Tension forces, because we have positive normal forces. Compression forces, yeah, simple truss structure. I think that's pretty clear. And here we can also see that this tension force is transported to that diagonal into that concrete column. Yeah. And now let's watch the shear forces. And here we can see at this hinge we have no additional tension forces, no normal forces. The same with the shear forces, you can see 0. And bending moments, again here the same, 0 bending moment. On the right side the same. Good. So I think we modeled it correctly. So let's continue with the other frames. Again, I want to adapt my work plane according to the size of my model. Now I want to copy it 2 times in the global Y direction. So I select everything, right click, move and copy. Number of copies is set to 2 and my displacement vector is in the global Y direction 9.5 meters. Good. I change here to the work plane XY. And now I want to add here additional beams. Yeah. Additional beams. Let's do that. New single member. And they get a new cross section, HEA 240. Material steel. And now I want to add here some hinges on both ends, so they will be connected as hinged beam, as truss, we can say, because we have on both ends hinges, moment hinges. Okay, so let's do that. So good. And the other nodes, they will get also new beams. For that, we create a new hinge. The member start should have here also at the start a new moment hinge, and at the end we can leave it as none because here we do another member hinge. So very easy. So now I want to copy that beams. I press my control key on my keyboard, select everything, and by drag and drop I can easily copy it. Good. Now I want to create here at that beams scissor hinges. What are scissor hinges? Scissor hinges, when you have four members connected, like here, for example. Here, 1, 2, 3, 4 members connected in one node. Yeah, I can consider scissor hinges, and each of the two member pairs transfer moments in its continuous member direction. But they do not transfer any moments to the other pair. So only shear forces I want to transfer to that beam. So when this continuous beam gets some loads, yeah, it will have a distribution of a moment, something like that. Yeah, so a support moment and a field moment, and I want to transfer only shear forces to that beam, to that upper chord. I have to create scissor hinges. Yeah, let's do that. So for that, I choose here these members. Member end should be a new cross section. Sorry. And now scissor hinge can be only created to my global coordination system. And here I have to activate the special type of hinge. And I want to consider the transfer of moments in my continuous direction. So I have to activate here the bending moments, and also I don't want to transfer any normal forces. So now, important thing, I have to activate here the UY direction, because I refer to my global system. I have to activate here the scissor hinge, and also one torsional hinge, because I don't want to have any torsional moments in my beams. I click on OK, and you will see here this S for scissor hinge, and we will do the same also for the other side. But here, member start, I choose here the global. So here we have this member scissor hinges, and and for the end of this beams, we create also a new type of cross sections of member hinges. Right click, member, edit, and here we create for the end these kind of hinges in order not to get any additional forces or moments. Good. Okay, so let's calculate this thing maybe in order to see if we modeled everything correctly. Maybe one note in order to have here I forgot here some bracings. We can create also here some bracings. So just click here on new single member. Change the member type to tension. I choose here a rolled cross section of the diameter of 20 millimeters. Click on OK. And create here this truss beams. So good. So now let's calculate this thing. So it takes some time. And let's look to the internal forces. Maybe according to the internal forces, I can you explain the scissor hinges again. So I choose here these 4 members and I want to explain you the scissor hinge again. So as you can see here we have our continuous beam, and here we have also a beam. And what I have done with the scissor hinge, I said, okay, please create me a scissor hinge that I transfer only my shear forces, so my vertical forces, to that beam in this direction, to the blue beam. And everything else, this should be considered in that continuous beam. And you can see no moment was transferred to the other beam. When we look to the shear forces, maybe here we can see, okay, here we have additional shear forces from that continuous beam. Yeah, and this is something important to know for the scissor hinges. Okay, good. Yeah, now I want to show you one additional information. When we look here, maybe to that beam, we see here the distribution of that bending moment, of that moment. And maybe you think, okay, this isn't correct because it has this distribution. This would mean that we have here a single force in the middle of this beam. Normally we have just the self weight, so it should be a quadratic distribution of that moment. When we change here on the calculation parameters, the number of divisions of members for the result diagrams, maybe to 30, we will get the right distribution. Let's calculate this again. Oh, now I calculate now every load case. I didn't. Doesn't matter. Now you see the right distribution of the moment. Yeah. So when you think, okay, the distribution of one of my systems isn't correct because it has the wrong distribution, then check please here on the the calculation parameters the right the right divisions of members for the result diagram. Okay, good. Now let's come to the load cases and loads. maybe before I do that, I forgot to mention that here at the calculation parameters, you have the possibility to check the deformation of failing members, and especially when you have nonlinear member types. And we have nonlinear member types because we have here this tension member types for the bracings. You can handle them when they fail, that they should be removed individually during the successive iterations. Yeah, this is maybe one important point when you have some systems or some models which have some instabilities. Then you can check here for that additional option and activate this, and maybe your model will calculate then. Okay, good. Now let's come to the load cases. I click here on new load case. I create here a new load case, impose load for the category A, then a new load case, snow, and the last load case, wind in the positive X direction. Again, let's take a look to the actions, imposed, snow, and yes, other things, combination expressions. I just want to consider here again the ultimate limit state, so I remove this serviceability, action combinations, yeah, and load combinations. This will be done automatically because we had set them before here in the basic data of our model. Click on OK. And now we add the loads on our structure. I choose here the right load case, and I want to add here some loads on that roof plane. For that, I go here to Tools, Generate Loads from Area Loads on Members via Plane. So in that case, first of all, I relate to my true area because I have now the self weight. The magnitude is 0.5 kilonewton per square meter, and now I choose the corner nodes so that I can get the boundary of my area load plane. Click on OK. Now I can remove the influence of members, and as you can see here on the work plane, at that moment everything is selected, also the upper chord, but I just want to consider the loads on the beams here, on the continuous beams, not on the upper chord, but just on that beams here. So I say remove the influence from members parallel to the upper chord, yeah? And you will see here now just these members are selected. Click on OK, and let's do the same thing then for the right side. So again, click on Tools, Generate Loads, and here we can see the program. It's the corner nodes from the last time. So if you if you create the new plane again, it has the same corner nodes, so you have to delete these nodes. Yeah, so I click here, delete current area plane. Now select the new corners. Click on OK. And now we say again, parallel to this upper chord, and click on OK. So now let's do this here also for that plane. Generate loads from area via plane. And here we have the same magnitude. I choose here the right nodes. And click on OK. So as we can see, here we have some information box about the generation of the loads. Click on OK. And when we click on the right click on display separately, we can see how the loads were added on our members. Yeah, good. Now jump to the next load case, impost loads. Click on generate loads again. And now it is our big advantage that RFEM remembered our last input of our corner nodes. Yeah, because now I can say, okay, please add here the same magnitude. Yeah. Click on OK. And we have here the same input of our load case impost loads. Good. Next load case, the snow load. Here I choose also my tools, generate loads, not here from area loads on members via plane, but we have also the possibility from snow loads on dual pitch roof. And here I choose the zone number. So first of all, I have to choose the right national annex. Yeah. I decide for Germany because we are located in Germany. I choose here the right information zone. In this case, I choose here Munich. I double click. The altitude is set to 550 meter. And now it's important to choose the roof geometry correctly. So in the right order, you see A, B, C, D, and so on. So clicking in the right order, C, D, E, F. And here we can see the new load case which will be generated in this load case. I want to remove some influence because, as you can see here, I just want to have my snow loads on that beams here. Members parallel to that upper chord, and click on OK. Good. Now let's do the same thing for the wind loads. For that, jump to the next load case, wind in positive X direction. Click on Tools, Generate Loads, Wind Loads. And here we have also the possibility to generate the wind loads on vertical walls with roof. I decide for the according to the Eurocode again, here for the national annex, we have also the possibility to consider another national annexes. Yeah. Wind zone here, I choose Munich, category 2, because I have maybe a little bit higher buildings in the city, in a bigger city. Again, here I choose the right base geometry. Now it's important that you do the base geometry in the right order as the roof type and geometry. Yeah? So start here again, here on the left lower corner, and when you want to select the roof type, you have to start at the same left upper corner. Yeah, as you can see it here in the right bitmap. So let's do this. And here the same. And because we have a very flat roof, the program will say to me that he will consider it as a flat roof for the wind pressures. So, and now we have the wind load case, wind in the positive X direction. So I say also that the wind should have the same side like the wind in positive X. So I delete here these members because I want to show it how it works. First of all, you can see here everything is selected, so every member is selected. For the wind, I don't want to consider here my upper chord, also not here this lower chord, and also not here these diagonals, and also not the verticals. So this was a wrong decision because the verticals are parallel to the concrete columns. So the program also deleted the selection of these concrete columns, but I want to consider my wind loads on these concrete columns. So sorry for that. I just do that parallel on that upper chord and on the lower chord. Click on OK. And the rest I do it manually. Just by the selection of this truss girder here. Okay, click on OK. Then click on OK again. And now let's see the different information about the wind loads. And here we can see the different wind loads on each member. Yeah, I think that's pretty clear. And now we want to consider these wind loads also in the other directions. And because we have already generated here these loads, we can easily copy these information to the next load cases considering wind load cases. So let's go to edit cases and combinations here in the symbol bar and click here on the load case 4, wind in positive X, and now we can easily copy them 3 times. Because now we want to consider the wind loads in every direction. So wind in -X, wind in positive Y direction, and in negative Y. Click on OK. And the only thing we have to modify is the direction of our generation wind tool. So double click on the generated wind loads and choose here the right side. Yeah. And in this case, it's from as a negative x direction. So DE. And you will see how it turns to the right direction. And the same thing we do for the other locations for the y direction. So positive y. So we need the side AFE or EFA. And let's do the same thing for the other side, so the minus y direction. So BCD. Okay. Good. So let's calculate everything. This will take some time. I drink some water during that calculation time.
Yeah, and just one hint from my side. Again, we are recording, so you don't have to worry. Like if you want to model this on your own, you will get the training recorded. Just once again, because we have this question asked many times.
Yeah, thank you for that hint, Ayla. As Ayla mentioned, you get the recording, their certificate, and also all the materials and the models. And this recording will be published also on YouTube, and there you can watch it. Good. Okay, now we have a problem because in some cases our model is unstable. Yeah, and this, I think it can be because of this hinges here. I have to correct them because I think I have here the wrong hinges. Let's correct them. Okay, let's calculate that again. So this will take some time. Okay. Sorry for the delay, but my PC is slow today. I don't know why. Yeah, and now it was calculated correctly. The reason was because I had here the wrong member hinges. Sorry for that, but now I think it's everything correct. Good. Now let's come to the explanation of the results. I would recommend you to do some plausibility checks. Yeah, so look to the internal forces, look to the deformations. Can this be right? And so on. So load case 1, self-weight. Can this be correctly? Can this be correct? So, okay, member hinges, I think that's pretty clear. So here we have there are places where we have member hinges. The bending moment should be 0. Here we have this scissor hinges. So with this support moment, field moments. Also our supports, they can act on some moments. I think that's pretty clear. Let's watch the deformation in UZ. Can this be correct? I think, yeah. Good. And so on, yeah. So when you do some plausibility checks, look to the deformations, look to the internal forces, and so on. Also to the support reactions, and so on. So let's do the steel design. For the steel design, we can use our add-on module RF Steel Eurocode 3. So let's open our add-on modules, design steel, and here we find RF Steel EC3, so Eurocode. Here we can design steel members according to the Eurocode 3. Let's click on that. And similar to our further add-on module RF Timber Pro, we can design different members and sets of members. First of all, I want to design all steel cross-sections, but just a design of cross-sections, no stability design, no stability design. So I choose here all members, but all steel members. So I go to the view navigator, click here on members by material, and activate just the steel material. Now I draw a selection window, click on OK, and I refer to the normal Eurocode. When you want to see some more information about some values, you can click here on this button, and you will get here some more information about different types of proofs, like here the general method when you want to make a stability design, or serviceability when you want to prove the deflections, and so on, the partial factors. Good. I want to consider my result combinations, so the combination of all results of the load combinations. Now I jump to the next material. Here we can see different material properties, cross sections, and so on. And also here some intermediate lateral restraints. So when you have here some additional members who fix maybe some beams, you can add here some lateral restraints. And also here, important for the stability design, effective lengths, you can set here the correct buckling lengths, and also the right lateral torsional, difficult word, also the right lengths for that. proof. But as I said before, for that case, we want to do only a cross-section design. So not stability. We can rename here this case, so just design of cross sections. And let's go to the details and deactivate here the stability analysis. Click on OK, and now watch here to that two windows on the left side. They will disappear because now we are just focusing on the cross-section design. I click here on calculation, and all members will be designed. And we can see here, okay, everything is good. So the cross sections are good enough. Yeah, good. And now the next check is the stability analysis. And for that, we have to create a new case. So, now I have a small problem. Sorry for that. Now, now I want to, I go back to my add-on module RF steel. And now I want to do a stability analysis of my upper chord of my truss girder structure here. So I create a new case, stability analysis of upper chord. I choose here this set of member because through the generation of our 2D truss, the upper chord was set automatically to a set of member. I click on OK. So, and now you see here we have, sorry, I have to choose the right result combination. And when I jump to this window, nodal supports for the set of member, we can see here our set of member. And if we want to perform a stability analysis, we have to define the right supports in that node, at that nodes. So in order to see it a little bit better, just click here on show figure or rendering. Sorry, click here on local coordinate system, and here we can see these supports. Yeah, these are the supports now for the stability analysis, especially for the buckling analysis and for the lateral torsional analysis. Let's calculate this and let's see if this works. And now we can see, this is not possible, non-designable, because when you look to the design, we have, this design is not good enough because we forgot to add an additional support at the middle of our upper chord. So we have to add an additional support for our proof of stability. And now I have to wait for my program again because it is loading. Now I want to add here in the middle of this, upper chord of this set of member an additional support. For that, I click here on that node, choose it from the model, and say, okay, let's do here an additional support, but I don't want to activate any rotational restraint, just an horizontal support, so a lateral support. I calculate it again, and now it works. And we can watch the eigenform of this of this case. Just click here on this icon, eigenform, and let's watch this eigenform of this beam. So this will take some time. Sorry for that. I don't know why, but my PC is a little bit slow today. So, and here we can see the eigenform. Here we activated the, here we have the supports, as you can see, Here just the lateral support, so just horizontal support, and here also the fixed support. And this is very interesting to see it how this will deform. Okay, this was the design, the very easy design of this steel hole. So what we have done, we did a cross-section design and then a stability analysis of our upper chord. Yeah. Ayla, any questions or anything to mention from your side?
No, I don't think so right now. But again, if you have any questions, you can write in a chat.
Okay, then I would say let's make a break again. Let's continue in 11 minutes. So in my time at 11:15, we continue our last example. Okay, so see you soon. Okay, can we continue, Ayla?
Yes, I'm here, and I think we can move on.
Okay, very good. So now let's come to our last project, to our last model. Maybe you can remember this was the model we modeled together in the second part of our online training for students. Now we do the design of these concrete surfaces, of these columns, and also of this downstand beam here. Yeah, good. So let's do this for our slabs. For that, we can use our add-on module RF concrete surfaces. So the design of concrete surfaces. You will find these add-on modules also here on the menu bar, design concrete, RF concrete surfaces. Let's click on that. So what we can see here in this window, we select first of all the result combination. Yeah. And then the right standard. We want to design here for the ultimate limit state according to the Eurocode. So no German national annex. For more information, you can edit parameters here. Yeah, but I think the presettings are pretty good for this first proof of concrete surfaces. So next thing, materials. Here you can see the used material, concrete C3037. On the right side, you see two bitmaps, the curve for the stress strain curve for the concrete here on the upper bitmap, and on the lower bitmap, you see the stress strain curve for the reinforcing steel. Here some additional informations like the modulus of elasticity or some compressive strength and so on. Yeah, next window is the surfaces. So which surfaces can be designed with this add-on module? You see here all surfaces. I think that's pretty clear. And now let's jump to the reinforcement. So this reinforcement window contains 5 tabs that control the reinforcement parameters. We define 2 reinforcement groups. So the first reinforcement group will be slabs. Therefore, we choose the right surfaces. We choose the bottom plate and also the upper slab. And the next part is here, reinforcement ratios. I think the presets are pretty good, so you don't have to modify there something. Reinforcement layout. Yeah, here you can adjust some additional things. For example, the concrete cover for reinforcement, you can do that according to a standard. When you edit, when you click here on edit, you see here this exposure class according to the standard. Yeah, here we can get some more information and so on. Yeah, but because we do here a very easy design, I don't need to consider this, so I let the values here to the new values here. I think that's pretty clear. Here the reinforcement directions, yeah, so once in the horizontal direction, then the other to the vertical direction. I think that's pretty clear. When you have different geometries of slabs, you can adjust here the directions. Let's jump to the longitudinal reinforcement. A difficult word here. Here we can set the provided basic reinforcement. Let's jump here to the reinforcement area due to rebar. Activate here for the top direction, so for the top location and also for the bottom location. Here we can, the rebar spacing should be 200 millimeter. Also here for both directions. And the reinforcement area is calculated automatically. We have also the possibility to choose one of our library something. For example, when you know the different Q and R meshes, you can choose also one of them. But this is something we do for the other reinforcement group. So I think the rest is okay. Let's do the reinforcement group for our walls. So for that, I click here, new reinforcement group. I write here walls, and I choose here the right surfaces. So these ones. And this one. Good. I click on OK. And for that case, I choose one of our meshes. I choose here the Q257A, both locations. Okay. Now I can jump to the last two register. You can set some minimum reinforcement due to the Eurocode or due to your standard, also the design method, and so on. There are a lot of options you can consider for your design, for your proof of these concrete structures. More you can find here in the handbook. When you press here F1 or here on the left corner side help, it will open this handbook, and you can find a lot of additional information about this add-on module. Also something about the theory. When I go here you'll find also a lot of theoretical background, and so on. This is maybe interesting when you want to inform yourself, but for that easy example, not mandatory. Good. Then let's calculate this. This will take some time. So what we can see here now. First of all, here the required enforcement. So what we have to put in our slabs, in our concrete slabs by surface. You get here an overview, but I would recommend you to use the graphics in order to see it better. So what we can see here now, jump to the results, click here on show reinforcement direction. And here we can see the different direction. I choose here the panel. Click here on OK. So this is the required reinforcement. What you have to do, what you have to put there. You see this direction, the other direction, how you have to put your reinforcements. When you want to have a better overview, maybe I would recommend you to change here this panel and say, okay, I want to consider here my rebar, then fill it up, and then you see just the reinforcement you have to put additionally to your base reinforcements, and how, as you can see here, especially at the near of the columns, you have to put there some additional reinforcements. Maybe you have to prove also a punching proof here, yeah, and so on. Yeah, what we can see here. Also here the shear reinforcements, and so on. Yeah, when you want to print something to your printout report, just select the right slab, click here on visibility by selected objects. Then I would recommend you to deactivate show hidden objects in background, view in Z direction, and give your technical drawer this PDFs or this prints here, and so on. Again, here I can choose 247, click on OK, and this is what your drawers or yourself need for the designing of this concrete surfaces. Yeah, so much to the design of concrete surfaces. Now let's jump to the next part, the design of beams. So for that, I changed the visibility mode. For designing beams, girders, columns, I can use RF concrete members. So as you know, we modeled in the last online training this downstand beam here. Important, this downstand beam was modeled as rib. So the member type was rib. When I click here on that member, you see here the member type rib. And important note on that place is that a rib, consider here this integration widths. So this rib, this beam, gets additional forces of the surface. Yeah, this is important to know. Good. Let's design this. So click here on RF concrete members. And here we have the same structure as in the RF concrete surface module before. We choose here the Euro code. We are designing for this one, for this result combination. And let's jump to the next part, materials. Yeah, I think that's pretty clear. Cross sections. We can also optimize here these cross sections. Ribs. Here we can see the effective widths. Also here in this bitmap. One important note on that case, we see, okay, and this rib is part of two members because we design here a set of member. And important when you design a set of member that you have the same effective widths. Otherwise, you will get some problems. And this program will not calculate this. Also here we have some supports. This is important to set the supports correctly. We will do that. So where we have supports here, also, here on that wall, and on that column, click on OK. So when I move this window a little bit lower, we can see, okay, this support number 38 is this wall support. It isn't an end support, but direct support we can do also on a lithic connection. Let's do that. And also for the other ones, we do a monolithic connection. So we have also the possibility to consider limited moment distribution of the support moment. Yeah, I think that's known of the concrete lectures of your study, or also of the Eurocode, and also a lot of other options. Let's jump to the reinforcement part. Here we choose the description and downstand beam, and we choose here the set of member. Okay, it's already chosen, so let's delete here these members. So which possible diameters do I want to have for my calculation? I choose here 60 millimeters and maybe also 25 millimeters. The maximum number of layers should be 1. The anchorage type should be straight, and curtail type should be, so we have no curtailment. Yeah, let's jump to the stirrups. Here we have the diameter 10 millimeters, inclination 90 degrees, so as standard. I would recommend you to use here the defined stirrup spacing. So what does it mean? So from the length of 50 to 300 millimeters, every 50 millimeters, according to the calculation, is 1 stirrup. Yeah, so now the next reinforcement layout. I would recommend you, because I want to have just the reinforcement here, just in the beam, not to activate here the distribution of, so over the complete slab. So deactivate this here. Yeah, so we have just the reinforcement in that beam. Here we can also consider the concrete cover, but for that easy example, I leave it here like that with 3 centimeters. minimum of reinforcement. I think that's clear. Here you can adjust some additional information also here, and so on. Good. Now let's calculate that. So this calculation will take some time. And as you can see here, the longitudinal reinforcements are listed on the top and on the bottom. Additionally, the torsional and shear reinforcements are displayed. Good. Here you can see also some additional information about this proof, about this design of this slab. Let's look to the provided reinforcement. So here we can see also a nice graphic of this structure, and also here the shear reinforcement. Yeah, also here the graphics, you can watch it also with the right effective width. Yeah, and this was a short introduction to that design of this downstand beam. Maybe one short note. Here you can see the required reinforcement, and here we can activate the provided reinforcement, and you see you are over this provided reinforcement is over this required reinforcement, and this is important. Good. So last but not least, the design of these concrete structures, of these concrete columns. For that, go back to data, click here on RF concrete members. And important to know is that the real code 2, so the design of concrete structures, provides 3 methods for the design of columns. We have the simplified method based on nominal curvature, the general method based on nonlinear analysis, including second order effects, and also the method based on nominal stiffness. Yeah, for our example, we create a new case. We create a new case and we apply the general method. For example, we do not have to use RF concrete columns. So we have also an additional add-on module for the design of columns, for concrete columns. But this add-on module is just for the nominal curvature method. Yeah. So I choose here the right standard. Also here the result combination again, and I activate here the nonlinear calculation. And this nonlinear calculation considers the effect of tension stiffening, so the behavior of concrete structures when they have when they are in the second order of concrete analysis. And I also want to consider creep and shrinkage. So I activate this here, and I jump here through the windows. I think this should be clear now. we don't need now any supports because we are calculating just the columns. Here at the reinforcements, I activate here the possible diameters of 20 and 25. Anchorage type should be straight, maximum number of layer 1. I enter here the description of concrete columns and activate just here the members which include really the concrete columns. So again here on view, I watch the concrete columns, cross section, and I choose here just here these columns, draw a selection window, click on OK, and jump to the next register, stirrups. Also here I define stirrup spacing. The reinforcement layout is here in that case in corners. So I want to have my reinforcements here in that in these corners. And yeah, and then calculate this. And here we can see it's not possible to design result combinations for nonlinear calculation. So I have to remove it and do it for the normal load combinations. So this will take some time, and after that we can watch the results. I think I calculated too much load combinations, but yeah, I think we will have it in a few minutes. Sorry for that. I have calculated too many load combinations. Normally, the load combination with the most pressure loads is that load case which will be the most important to design. But now we have combination 9, so the last one will be combination 10, and after that we have it and we can watch the results. Short hint on that place is that the nonlinear calculation will take a longer time than the normal calculation. But now I'm pretty sure we have it. If not, I cancel this and calculate it only for one load combination. Okay. I cancel this because this takes too much time. But it has already calculated for some points. So here you can see, here we can, yeah, Here we can see that for almost all columns, the required enforcement can be covered by the minimum reinforcement for compression members. And if you look here for this message or note, you see, first of all, we have a corner reinforcement, so the hint 22, and 25 is the minimum reinforcement for compression members according to the Eurocode. And also here we can watch the reinforcements by graphic, and also what we have here as provided reinforcement and as required. And the required is just the minimum reinforcement. Let's look it here. So we cancel the visibility mode. We see here the different reinforcements. Good. So this was the last part of this training. I hope you enjoyed that training. You learned something. We gave you the basic knowledge of the design of easy structures in every engineering area. So we had timber structures, we had steel structures, and we had also concrete structures. And now I think as students, you are well prepared for further steps with RFEM, especially when you do some designs and so on. Yeah. Ayla, anything from your side?
No, I think it's pretty clear so far. So I also hope you could learn something, especially with designing structures. And thank you for joining us. And again, if you have any questions, you can still ask them.
Good. I just want you to show you our website. So if you have any questions or you want to know something, visit our website. And you have here the possibility to get a lot of new information. When you click here on support and learning, you can visit frequently asked questions, or you can visit some knowledge base where we explain you the most important things considering the design of timber structures or concrete structures and so on. If you want to train the program better yourself, I would recommend you to visit this education. Here you have the possibility to watch the RFEM 5 for Beginners course. Also here, a lot of recorded webinars, or I can recommend you also a new webinar. When I go here to webinars, I really recommend you, when you are interested in to watch and visit the free webinar Stability Design in Steel Constructions with RFEM and RSTOP. My colleague Andreas will do that. I can really recommend this. And yeah, then I would say it was a lot of fun with you, and thanks for watching, and stay healthy. And I hope we will see you the next time. And as we said before, you get the recording, the materials, and everything else. Also the certificate, important for your CV. Yeah, so from my side, goodbye and see you soon.